Hi guys, my name is Farhan Khan and this is my project OTAPS, an open source train accident prevention system for the Indian Railways. This project has been made for the Circuit Digest IoT and Edge AI contest. My project required a Wi-Fi cable board to allow the station master to control and monitor the passage of trains. And Digikey has been super nice by providing me with an Arduino Uno Alpha Wi-Fi board free of charge to build this project. Thank you so much Digikey and Circuit Digest for providing me with this opportunity to showcase my talent to the world. Now let's go over the contents of this project. This video has been divided into 3 chapters. In the first section, we are going to look at what OTAPS is and how it can speed up railway safety. In the second section, we are going to look at how some of the recent train accidents could have been averted with the help of OTAPS. Lastly, we are going to cover how OTAPS work and its various components. The obvious question you might have is, what is OTAPS and why should we even consider using it? To answer the first question, OTAPS is an open source train accident prevention system designed with a goal to be an alternative TCAS, also known as KAVACH. It consists of 3 parts: the signal unit, the locomotive unit for the locopilot, and the web interface for the station master. The web interface allows the station master to view and control the state of the signal units. The Arduino Uno R4 from Digikey acts as the bridge between the web interface and the signal units. I will go into more detail on these in a later section. In the past few months and years, the Indian Railways has suffered a lot of train collisions. One of the primary reasons for many such accidents is the absence of TCAS or KAVACH on those routes. So far, only around 1500 km of the railway network has been fitted with KAVACH, which accounts for just 3% of the railway network. One of the major reasons for the slow progress is the high installation cost of 50 lakh or 5 million Indian rupees per kilometer of the track and 70 lakh or 7 million Indian rupees per locomotive. OTAPS on the other hand has an installation cost of just rupees 8,000 per kilometer of track and 4,000 per locomotive, which is just 0.16% and 0.05% of the cost of installation of TCAS. The best part about OTAPS is that it can be installed on routes that do not have any automatic signals installed, as it is capable of working independently. The power consumption during operation is under 1 watt. This makes it possible to simply power it from a solar panel and a battery, thereby eliminating the need for any external electrical infrastructure. In the next section, I will go over some recent train accidents and how it could have been prevented with the help of OTAPS. On 2nd of June 2024 at 3:15 am, train number UP-GVGN, a freight train, collided with another freight train from behind which was stationary at the Sirhind junction in Punjab. Investigation revealed that both the locopilot and the assistant locopilot of the UP-GVGN had dozed off, overshooting a red signal. By the time the locopilot saw the stationary train, it was too late. The VAC-12 locomotive of the UP-GVGN rammed into the stationary freight locomotive, leaving the locopilot and the assistant locopilot severely injured. A similar pattern was seen for the 13174 Kanchenjunga train accident which occurred on 17th of June 2024 in West Bengal. I have set up a similar scenario here to showcase how OTAPS can prevent such an accident. Consider the stationary locomotive at B as the freight locomotive at Sirhind Junction, and the other at station A as the UP-GVGN locomotive. The state of the home signal is red and the signals after it are green, double yellow, yellow and red. Now I will clear the home signal from the web interface to allow the locomotive at station A to move. The locomotive crosses signal 1 with full speed. As it crosses signal 2, it sees that the signal ahead is double yellow and yellow, so it reduces the speed of the locomotive and crosses signal 3. Just as it crosses signal 4, it sees that the signal ahead is red and it automatically applies the brakes and brings the locomotive to a halt, thus preventing a collision. The screen on the locomotive shows that the locomotive has stopped and the line is blocked. Let's look at another scenario where 2 trains are moving towards each other on the same track. I have one locomotive at node A and another at B, and all the signals are green. Both the locomotive cross the first green signal at full speed, but as they cross the second one, both of them sense that there is an incoming train and immediately applies the brake to prevent a collision. You can see on the screen of the locomotive A that the locomotive has stopped and the line is blocked. It also shows the state of the signals ahead, which is green, red and yellow. The locomotive unit of the locomotive B shows the same information. Now that we have looked at the demonstration, Let's go over the various components of this project and how they function together. I'll keep the explanation brief enough to provide a high-level understanding of how things work. I won't be going into the absolute detail about the working of the system, as all of that is thoroughly documented on the article for this project. The documentation for this project is well over 100 pages long and covers every aspect of the project. From the communication protocol, payload format to the interface of the web UI, signal and locomotive unit, explanation of the schematic and assembly instructions to the explanation of code, programming and demonstration itself. Coming back to the initial topic, OTAPS consists of three parts: the signal unit, the locomotive unit and the web interface. The signal units communicate the state of the railway line to the locomotive unit. They are placed alongside the railway tracks. The signal unit transmits its own state as well as the state of the three signal units before and after it. 3 is not a fixed limit, but since I could only make 5 signal units due to a limited budget, I chose 3 as the sweet spot. This can be increased further with minimal changes. To detect that a train is passing, they use these NPN proximity sensors to count the axles of the locomotive. In a nutshell, the signal unit acts as the 4-aspect automatic signals used by the Indian Railways, with the added capability of transmitting their state as well as the state of the other signal units wirelessly. The first and the last signal units are paired with an Arduino Uno R4 Wi-Fi board to transfer the data between the web dashboard and the signal units. The web dashboard contains information regarding the signal state, number of axles, as well as it allows changing the signal state. This is the locomotive unit, which is fitted on the locomotive. It performs 3 operations: slowing the train when approaching a yellow signal, applying the brakes when approaching a red signal, applying the brakes when 2 trains end up on the same track and are moving towards each other. The signal units send their state as well as the state of the next 3 signals to the locomotive unit. So at any instance, the locomotive unit knows the state of the next 4 signals. This is the reason why in the collision demonstration, both the locomotives were able to identify an incoming train, even though the next signal was green. This picture shows what the various elements on the UI mean. Now that we have looked at the locomotive unit, let's look at the last piece of the puzzle, which is the web UI. It is made using the Blink platform. The web UI allows the station master to control and monitor the state of the signals. It has 4 widgets, and this is what they do. The Arduino Uno R4 Wi-Fi acts as the bridge between the web interface and the signal units. The data transfer between the Arduino and the signal unit is done via I2C. The Arduino sends the data received from the web interface to the signal unit, as well as it sends the signal state and axle counter values from the signal unit to the web interface. Now let's piece everything together and go for one last demonstration. I have put together this setup. The ice cream sticks act as the guide rail for the locomotive. The proximity sensors are mounted at an appropriate height. The signal units count the axles of the locomotive using the inductive proximity sensors. But the toy locomotive that I am using for demonstration is made of plastic. So I have taped some metal coins to the side to simulate the metal wheel of a real locomotive. The locomotive is placed at station A. All the signals except the home signal are green. I will clear the home signal from the web UI to flag off the locomotive. Notice the axle counter and the signal state changing as the locomotive crosses the signal units. Now to clear all the signals between the stations, I can press the signal reset button on the web UI. For more information on this project, consider looking at the documentation on the website. It should go live on 11th of November. I will add a link to the article when it goes live. The code and the PCB files are available on the GitHub repositories. Anyways, this has been a project OTAPS and I hope you enjoyed looking at it. Thank you for watching and I'll see you again with some cool projects.